So welcome again to the second session of the revision class for the principle of food technology. And in the second section, we will be covering the physical properties, state of matter, and energy balance in food processing operation. And here we'll be looking at energy balance in food processing, solving simple problems involving works, energy, power, heat capacity, enthalpy, state of matter, and sensible and latent heat. Yes, you can see me because I'm using a desktop now. I'm using a desktop. The laptop broke down, so that's why you can see me now. I'm sorry. So that's the problem. I'm using a desktop. So, but can you hear me loud and clear? Okay, good. That's good. So we will be looking at during the study week in the material we mentioned that sensible heat changes. We can see a change in temperature. For example, from here, we could see a change in temperature. You could see there's a change in temperature here, and to here. But latent, there's no change in temperature. So there's a difference between the two. So we should understand that. So in sensible heat, there's a change in temperature. In latent, there's no change in temperature. The temperature remains the same. Sensible again, you could see a change. And the latent is all about phase change. From solid to liquid, from liquid to gas. So we have that phase change. And because of the phase change, they are not accompanied by a change in temperature. So I want us to take note of that. And then in our specific heat capacity is it has something to do with the sensible heat, and I will explain that. Now, is measured in joule per kilogram per Kelvin. Now, if you look at my unit here, joule is in capital, kilo here is in small letter, and Kelvin is in capital letter. So energy now, and it is measured in that unit, and it's the energy required to raise the temperature of 1 kilogram of substance by 1 Kelvin. Now, because if you look at this, if you look at the formula, you can actually tell me the definition of specific capacity. The energy required to raise the temperature of 1 kilogram in 1 Kelvin. Looking at the unit, you can tell me the definition. And for example, if the heat capacity of a fruit juice is 4,000 joule per kilogram per Kelvin, it means that 4,000 joules of thermal energy is required to raise the temperature of 1 kilogram of that fruit by 1 Kelvin. That's the meaning. And then we also said that heat supply to food material is defined by mass of the material multiplied by specific capacity of the material multiplied by temperature change. Now, when there is temperature change, yes, this formula is right. This is the formula you will use to calculate the heat supply to a material. But when there's no temperature change, are we going to say that the heat supply is zero? No, the heat supply cannot be zero, because when there's no temperature change, this is going to be zero and Q will be zero. But we cannot say that it's going to be zero. So there's another formula you use for when you're having latent heat situation. Now this is for sensible heat situation because we could see a change in temperature. Now, if it is a latent, let's look at what is going to happen. Now, if it's a latent, the formula you're going to use if it's a latent is given as Q equals ml, mass multiplied by latent heat of vaporization or by latent heat of fusion, depending on the change of state. If it is changing from solid to liquid, we talk about fusion. If it is changing from liquid to gas, we talk about vaporization. So take note of this formula. If it is, you need to take note of the formula that if you are dealing with latent heat, your Q equals ml. Under latent here, and here, your Q equals ml. But here, when it is sensible heat, when it is sensible heat, your Q equals mc, change in temperature, mass multiplied by specific capacity multiplied by change in temperature. Now, looking at the unit of Q of latent heat changes. Now we know that our Q equals ml. Now, our L is latency of fusion or vaporization. Now, looking at this formula, so to know the unit of L, the latent heat of fusion or vaporization, to know the unit of L, you will know that Q is in joule, M is in kilogram. So the unit of L will be joule per kilogram. So that is in joule per kilogram. So that one is different from the unit of specific capacity. The unit of specific capacity is joule per kilogram per Kelvin. But the unit of latent heat of vaporization is joule per kilogram, as we have shown here. So let's take note of that. So moving forward, now this is a typical example. Now imagine that we have 1 kilogram of water at 20 degrees Celsius in a pan. What is the amount of energy do we need to input into the system so that the water starts boiling at 100? Now, we have 1 kilogram of water and it is at 20 degrees Celsius. Now, what is the amount of energy we need to input into the system so that the water starts boiling at 100? Now, the question says so that the water starts boiling. Now, we want to heat up the water to 100. So we are interested in at that point when it starts boiling. So we're not interested in when it's turning to gas, into gaseous state. We are interested in when it starts boiling. So what is the amount of energy do we need to input into the system? Now, we know that specific heat capacity that is given to us as this. That's the specific capacity of water. And this can be in different form. It can be in joule. It can be in kilojoule. Sorry, this K should be in small letter. This K should be in kilojoule, small letter K. So that's the problem from word. So this should be in kilo. This is not Kelvin, because if this is in capital letter K, it can be misinterpreted as Kelvin. So in small letter K, kilojoule. So this should be kilojoule. So just as I have it here, kilogram then kilojoule. So we need to watch those books. Sometimes some of the books we have that the mistake can come from some of the books. So we have that. So we want to find out. No, we know that the solution is we have a change from 20 to 100, and that tells us that a change in temperature is 100 minus 20, which is 80 Kelvin. Now, and we know that that is 8K. We know that our Q equals MC, change in temperature. So we have our Q to the mass. The mass is 1 kilogram. The specific capacity is 4.19. Then the temperature is 80. So our final answer is, when you multiply everything together, is 335.2 kilojoule. So all you just need here is to use a calculator. So we need to add 335.2 kilojoule of heat energy to raise the temperature of water from 20 to 100 degrees Celsius. That's how you do that. This is the simplest version of heat energy calculation. Now let's look at a more complex situation. Now we have 100 kilogram of ice. So I don't know, this unit is correct. Now this one is correct. It's kilojoule per kilogram. Yeah, good. This one is correct. The SI unit here is correct. I'm only referring to the SI unit in this place. So now let's look at the question as a whole. 100 kilogram of ice at 0 degrees Celsius is placed in a vessel and it is heated until it is all of it is converted to steam at 100 degrees Celsius. Sorry, there's a mistake there. Then until everything is converted to 100 to steam at 100 degrees Celsius. How much energy is required to do this? Now the specific capacity is given to us as this. The latency of vaporization of water or latency of vaporization is given to us as this. The latency of crystallization of water or latency of fusion is given to us as this, 334 kilojoule per kilogram. Now, the very first thing we want to do is to write out the given. We are given the mass of ice, the temperature change in different phases, and we want to calculate the energy supply. So what we need to do is to look at we know that we are giving the ice at 0 degrees. Their ice we turn to water first at 0. So don't forget there will be initially because we are starting from ice at 0. So we need to go to water at 0. That's talking about latent heat changes. That's a latent phase. So from water at 0, we will now move to water at 100 degrees Celsius. And from water at 100 degrees Celsius, we will now move to steam at 100 degrees Celsius. We need to know those stages. We must not miss out any stage. If you miss out any of those stages, we won't be able to get the final answer right. So just like we have it in our module coursework, all the stages are very, very important. So we are moving from 100 kilogram of ice at 0 degrees Celsius, and the way to do that is to have a box such as this. So we want to look at energy from 0 to 0 ice, 0 at ice, and to 0 at water. Then from 0 at water to 100 degrees Celsius at water, and then from water 100 to steam 100. That is where we are going to stop, because this one does not involve superheated steam. So, and it's not starting from, and this is the starting point, because here we were not told that the ice is at minus 20 or minus 20 degrees Celsius. No, we're told that the ice is at 0 degrees Celsius. So we're going to start at 0. So this is straightforward. So, and all we now need to do is to look at the appropriate formula for each of the stages. Now for this stage, we are talking about latent, so we need to use ml. Now you now need to decide which one are you going to use, is it fusion or vaporization? But here we are having ice, solid, changing to liquid, water, so it's fusion here. Here, water is changing to steam, so it's going to be what here? Vaporization. Here is a sensible state, sensible heat changes. So it's going to be MC, change in temperature, mass of water or mass of the ice that is converted to water, specific capacity of water, and then change in temperature. Here we will not be using specific capacity of ice, because here is that in this state it is water at this point in time. It is no longer ice. So here we will definitely be using the specific capacity of water. Deliberately, I might give you specific capacity of ice here, but it is not needed in this question, because we are not moving from minus 20. We are moving from 0. So we only need to use L of fusion, here specific capacity of water, then L of vaporization. So all we need to do is just to go back to what has been given to us. M for everything is 100 kilogram. And L of fusion is latent heat of crystallization of water, which is this one, 334. So we have that there. But now this is in kilojoule, but we are having it in joule. So we need to have the 30. Then energy required to change the water from 0 to 100, MC theta. Mass, the same thing. Specific capacity of water is 4190 joule per kilogram per Kelvin. And the change in temperature here is 100 minus 0. And here, finally, we have a ml. Mass, latent of vaporization. Mass is still the same thing. And the latent of vaporization is given to us as 2256. So we put that there. But now, because we are calculating everything in joule, so we want to be consistent, we add additional 30 to have it in joule per kilogram. All we need to do now is to use a calculator. So when you use a calculator, we have this multiplied plus this. Then we have the total energy now to be 300,900 kilojoule. So that's how we find the amount of energy required to convert 100 kilogram of ice at 0 degrees Celsius to steam at 100 degrees Celsius. Do you have any question? Any question, Chris? Is it clear, Chris? Good. So moving forward, so this is the last component of the module, which is talking about the Piscal. Welcome. Sorry, we had issues with them. We had issue with the technology the other time. So and the laptop, I think the laptop was having issues. So good. Thank you. I think other might be struggling to join as well. Now, what we've done, we've completed one session before you join us. What I will do, I will continue with this session, so that when I finish this session, I'll go back to session 6, session 6 again. So you came just in time. So we'll start with the session 7, then we'll go back to section 6 once we finish everything. So section 7, we go back to section 6, sorry. So section 6 is talking about the state of matters. So section 7 is talking about the Reynolds number. Here we want to understand the significance of Reynolds number in food processing operation, understanding of laminar and turbulent flow in food processing based on Reynolds number. So what we'll do here is to look at what do we need to calculate our Reynolds number. Now, first of all, we all need to know the velocity of the fluid. Now, sometimes this can be very difficult in real life in the food industry. For example, we are not measuring how fast your car is or how far you are driving. No. So velocity might be difficult, might not be relevant. So what I think will be relevant to most of us in the food industry will be volumetric flow rate. Now, when we're talking about volumetric flow rate, yes, now we are on the same page. But when we're talking about speed of processing food, no, we are not. That's going to be when you're talking about distance. It's confusing. Distance divided by time is going to be confusing when you're talking about food. So when you're talking about flow rate, yes, we are on the same page. So as a result of that, but unfortunately, in our Reynolds number, I'll come back. In our Reynolds number, we have velocity as one of the parameters. We have velocity as one of the parameters. So that's what we have in our Reynolds number. But in the food industry, we'll be talking about volumetric flow rate. So now the question is, the reason why you have this page and this page as well is to look at how do we convert our volumetric flow rate to the velocity. Because if you are given this in the question, for example, you need to know how to convert that to this before you can use it for your Reynolds number. So we need to look at how we do that. Now, the difference between the two, this is talking about distance over time, the velocity. Volumetric flow rate is talking about the volume per time, the volume of flow per time. And you could see from their unit, this one is talking about distance per time. You can see from their unit meter per second. This one is talking about volume per time. You can see from the unit meter cube per second. Now, you could see from that unit, you could see what you need to multiply or what you need to divide by. Now, I could see from here, if I multiply this one by area, if I multiply my velocity by area, I will get the volumetric flow rate. Because my area is in meter square, so if I multiply that by meter square, I will get the volumetric flow rate. Let's look at how it's done. So volumetric flow rate is therefore defined as velocity multiplied by a cross-sectional area of pipe. So we have that as velocity multiplied by cross-sectional area of pipe. Now cross-sectional area, like I remember Yabrina, you mentioned earlier that in the question you are in the material we have per r square, and I was using pi d square over 4. You can see they are the same thing. It doesn't really matter. Use any of them, any that you think you are comfortable with, you will get the same answer. You get the same thing. So cross-sectional area, they are the same thing. Pi r square, pi d square over 4, the same thing. But don't forget, when you are using this, do not forget to take your 4 along. Do not leave your 4 behind. It is not pi d square. It is pi d square over 4. And I can actually prove that for us. That if you, and I know you can do that. If you look at your area, look at your area now. Sorry, let me just see. You know that area equals per r square. Don't forget that your r equals diameter over 2. That's your r. Your radius is diameter over 2. So don't forget that on top of that you have your square. You have your square. So this will now equals to pi d square all over 2 square is what? 4. So you can see this and this, they are the same thing. So they are the same thing. So I think that's clear. All right. Good. So once you have that, the most important thing here, the most important thing I want you to really remember here is that your volumetric flow rate is defined as velocity multiplied by cross-sectional area. So the reason for that is if you want to calculate your Reynolds number, you need to use velocity, not volumetric flow rate. then density is also important, and the diameter of the pipe is also important, and the viscosity, dynamic viscosity, is also very important. This is the formula for your Reynolds number, and it's defined. This V is your velocity. You can see the unit is in meter per second, not meter cube per second. So it is not flow rate, it is velocity. So if you are giving velocity, that is perfect. Use it. If you are giving flow rate, you need to look out for your cross-sectional area and use that to calculate your velocity. Then now use that to calculate your Reynolds number once you have your density, diameter, and this dynamic viscosity. These are things that you need to know about Reynolds number, and I will tell you more things that you need to know. Now, let's look at an example, because it's always good to calculate, to illustrate using an example. Look at this. Now, if your Reynolds number, if your Reynolds number is less than 2300, you need to know this number. This is laminar. If it is less, it is laminar. If it is more than 4000, it is turbulent. So the two numbers that are important here is 2300 and 4000. Forget about any other thing. What you need to know here is 2300 and 4000. Now, if it is less than 2300, it is laminar, very gentle flow. If it is more than 4000, it is turbulent. And if it is in between the two of them, if it is in between, the flow cannot be predicted. I'm not interested in testing how that. I'm not interested in testing this. So it's either it is laminar or turbulent. But in between, we know for sure that you cannot predict the flow. So, we'll talk about when this is very important. If you are doing cleaning, it's cleaning operation. If you are doing cleaning in place in your equipment, you want the flow to be turbulent because you want a rigorous contact between the cleaning fluid, a rigorous mixture between the cleaning fluid, cleaning agent, and what you are trying to clean. We want them to be rigorous. We want that to be rigorous. So you want that flow to be turbulent. But if you are trying to separate components, maybe you are trying to do sedimentation, or you are trying to crystallize out a component from maybe something that happened in pharmaceutical industry, crystallization. You want a flow that is laminar, very gentle flow, so that you can have a deposition of the component you want to get out of the system. So, well, when you are doing cleaning, when you are doing mixing, you want it to be turbulent. You want a thorough mixing of the components. So we are talking about turbulent flow. So now let's look at this example. What is the condition of the flow in the following pipeline? Water flowing at a rate of 1 meter per second. This is a very simple question because this is given to us in velocity. We don't need to do any conversion. So if it is not given to us in velocity, don't forget we need to do the conversion by saying that your volumetric flow rate equals velocity multiplied by area, and therefore your velocity will be volumetric flow rate divided by area. So you know the area, the cross-sectional area. And how do you know the area? You know the area from the diameter. If the diameter is given to you, the area is known. Question? Yes, I'm listening, Chris. Don't forget to switch on your mic. I can't hear you. Okay, what does -1 mean? Oh, now this one, what does yeah. Now what this means is this. Now this is just talking about you. That's a very, very good question. That tells me that you are following me, Chris. Let me show you. Now it's just its unit. It's you know, I can say that my velocity is measured in meter per second, or my velocity is measured in meter per second. I can write that one as this. Okay, that -1 is raised to power. It is not this. This is not this. This is not this is not it. Okay, this is cancel. It is not this. It is meter raised to power. Look at this. It's power. And this, they are the same thing. Okay? It's the same thing as writing. Okay, good. So it's just the unit. Okay? Wonderful. So this is the way of writing our velocity. Thank you. So we have the velocity, we have the diameter of the pipe, and like I said earlier, if this has been given to us as a flow rate, so we need to convert that to velocity by dividing by area, and area we can get from what? From the diameter. Diameter square divided by 4. You get your area. Pi, diameter pi, this square over 4, that will give us the area. Then you use that just like in the formula I've given to you. And like I said, formula sheet that will be provided for you is already there. So you don't need to count them. But it's not, if you use them from time to time, you don't even need the formula sheet. Then the density is given to us. Fine. Now the reason why I said this question is very straightforward is that all of the parameters given to us, they are in SI units. You can see SI units, SI units, SI units. There's no need to do any conversion. Because if they are not in SI units, you need to do a conversion for them. Now, the reason for that, you may be buying a particular product from states, and they are giving their units in maybe the unit they are familiar with, which is not in SI unit. So don't forget, you need to do your conversion in SI unit if it is not given in SI unit to determine the flow condition. So now look at solving the problem. So we've been given the density, the velocity. You can see me again now, Chris. You can see this is velocity. This is another velocity. So you can see the units. They mean the same thing. But what I cannot write is to write it this way. I cannot write it this way. Look at this. I cannot write. This is like saying tautology in English language. It's like saying, this is like saying MX. Because you've applied this is like saying MS. You've applied this division twice. So you cannot say this at all. Please just take note of that. It is one or the other. So we have the velocity, we have the diameter, we have the dynamic viscosity, and the Reynolds number is known. This is the formula. Then you have the density is given, velocity is given, we have the diameter, we have the dynamic velocity. The rest is your calculator. Just use your calculator, punch it, and then punch the figures into the calculator, and then you have this as a number. And from this value, we can see is massive, is greater than 4,000. So the flow is turbulent. Okay. Yes, question. I'm listening. We are listening, Yavenda. Now, what is the unit of Reynolds number? Now, can somebody tell me the unit of Reynolds number? I'm expecting text from Fiska and Chris. What is the unit of Reynolds number? Fiska said no unit. Chris, do you agree with that? Yes. Chris, do you agree with that? I've not received your response, Chris. Fiska said Reynolds numbers has no unit. Do you agree with that, Chris? Yes, no unit. Yeah, Yavenda, like we said, Reynolds number has no unit. Reynolds number is a dimensionless number. And as a result of that, it has no unit. You've asked a very, very interesting question here. It has no unit. Now we can show that, but I'm just looking at the time now. We can show that, but it has no unit, like we said earlier. I think I demonstrated that during the study week. But it has no unit. If you put these units together, kilogram per meter cube, this one here, and if you put all these units, let me see. If you put this kilogram per meter cube, meter per second, meter, and you multiply all of them together, divided by Newton seconds meter square, we will discover that it has no unit. They will all cancel out each other. So Reynolds number has no unit, but I'm not interested in that. But just know that they have no unit. It is a dimensionless number. So I think that's the end of the revision. That's the end of the revision. But before I go, let me quickly go. Before I tell you the final hint, is that okay if I go through Chris and Yavenda? Is it okay if I go through session 6 again? Oh, good. Thank you. So session 6, which is not, it's already recorded, but Fiska missed that because of the problem that we had with the technology. So what we need to note here is the physical properties, state of matters, energy balance in food processing. And we said during the study week, during the lecture, we said that we need to know that there are two different changes. We have sensible and latent. Sensible heat changes, they are the ones that you will see a change in temperature. You could see from T1 to T melting. So you can see a change in temperature. But latent, you could see the temperature remains the same during latent heat. But you are actually supplying the heat, but the temperature remains the same. Sensible heat, again, you could see a change in temperature. So you should know the difference between the two, because when you are calculating your heat supply, you use different formula for latent and for sensible heat changes. Now for sensible heat changes, the formula for your quantity of heat supply will have change in temperature. But latent heat, they will not be changing them. Otherwise, if there's a change in temperature of 0, and so that shows that energy is not supplied. That would be 0, but it's not. Energy is supplied, but it's only doing something else. The energy that is supplied at that point in time, at that latent heat changes, that energy is breaking down the structure of the molecule. Now, because the molecule is changing, for example, solid is changing to liquid. So the energy that you are supplying at that point in time is only breaking down the solid molecule into liquid molecule. So that is why you are not seeing a change in temperature. The energy is massive. Even if from your calculation, you will see that the energy is a lot of energy. So, and we said that specific capacity, it is measured in joule per kilogram per Kelvin. And from this unit, we could say, we could quickly see that energy required is the energy required to raise, the specific capacity is the energy required to raise the temperature of that substance, of 1 kilogram of that substance by 1 Kelvin. Now, for example, we are saying that the specific capacity of fruit juice is 4,000 joule per Kelvin, joule per kilogram per Kelvin. What we are saying in essence is that it means that 4,000 joule of thermal energy is required to raise the temperature of 1 kilogram by 1 Kelvin. That is the meaning, and that's the interpretation. And I got that interpretation from this unit. 4,000 joules of thermal energy is required to raise the temperature of 1 kilogram of fruit juice by 1 Kelvin. Looking at the unit, and we said that this applies to food material is defined as the mass of the material, specific capacity, temperature changes. And I said this is only limited to sensible heat changes. For latent heat changes, there's no change in temperature, therefore you will use a different formula for that. And the formula to use for latent heat changes is Q equals ml, mass of the substance multiplied by latent heat, whether is either for fusion or vaporization. And we said something about the unit. The unit of the specific capacity is joule per kilogram per Kelvin. For latent heat of fusion or vaporization, the unit of this one will be joule per kilogram, because we could see from this formula we could derive out the unit from this formula. Let me show you how I did that. So we could derive the formula from here. Our L equals Q over M. Our Q equals joule. Our M is measured in mass, is in kilograms. So joule per kilogram. That's although this is going to be given to us as a constant anyway. So for example, in this one now, I've given you the specific capacity of water to the joule per kilogram per Kelvin, and I said this is a mistake. This should be small letter K for this one. It's not capital letter K, because you only have your K, capital letter K, in Kelvin. So the question says we have 1 kilogram of water at 20 degrees Celsius in a pan. What is the amount of energy do we need to input into the system so that the water starts boiling at 100? Now we are asking for what is the amount of energy required to change water from 20 to water at 100. That is what we are asking for. Here there's no change of state. It's only water to water, but first at 20, then second at 100. So what we need is to have specific capacity formula, which is a Q equals mass of water multiplied by specific capacity multiplied by change in temperature. So this is what we need. We know that change in temperature is 80 K. So we know that mass is 1 kilogram. Specific capacity that has been given to us as this 4190 joule per kilogram, and that will be 4.19 kilojoule. Sorry, this kilojoule here is small letter. This should be small letter. So it's small letter K. kilojoule per kilogram, and this K also is small letter. It should be kilojoule kilogram, small letter. I think when you copy sometimes when you copy something from Word and you put it in PowerPoint, that may be an issue. I need to watch that next time. So this is in kilojoule, small letter K, small letter K. Now, so we have that 80 Kelvin. Now we multiply mass, specific capacity, multiplied by 80. So we have this. If you use a calculator, you have this 335.2 kilojoule. So that is the amount of energy we need to add. This is a simple one. Now moving forward. Now this one is asking 100 kilogram of ice at 0 degrees Celsius. Now we want to change that to steam at 100 degrees Celsius. From 100 kilogram of ice to steam at 100 degrees Celsius. The question says how much energy is required to do this. Now we need to do this stage by stage because we are moving from ice at 0 to water at 0. Because if you miss any step, there will be a problem. We won't get the final answer right. So we are moving from ice at 0, then we change to water at 0, then from water at 0 to water at 100. That is the and then we are going to steam. So we now need to move from steam at 100. We now need to move from water at 100 to steam at 100. To make it easy, it's always good to have this diagram. So first of all, we have the total energy supply. This is the starting point. We are moving from ice at 0 to water at 0. Then water at 0 to water at 100, and from water at 100 to steam at 100. That is where we're going to stop. Because we've not been told that it's superheated steam at 120 or at 150. If we were told that it's superheated steam at 150, then we will not say steam at 100 to superheated steam at 150. Now here again, we started from 0. We did not start from minus 20. So we did not say minus 20 degrees for ice to ice at 0, but because the ice is starting from 0. So you look at the question, and the question will allow you to know what are the stages involved. But please be careful. Do not miss out any of the stages. For example, it might be very easy for us to miss out the latent heat changes. Here, it's not very easy to miss these changes, but they are very, very, very vital. Look at it, for example. Look at latent heat of fusion here. Look at it. Very high amount of energy. Again, 225 million, very high amount of energy compared to 41. So you can see a change from 0 to 100, 41, but no change in temperature, but it's a change of phase. A change of phase from water to steam, massive amount of energy is required. A change of phase from ice to water, massive amount of energy is required. Now here the temperature is still at 0. Here the temperature is still at 100, but because it's a change of phase, massive amount of energy. If this is missed out in the computation, you know the answer will not be correct. So let's take note of the phase changes. So here changes from 0 to 0, ice to water. Then we have 100 because the mass is the same. We use the same mass. So we have here, what we're going to use here is latent heat of fusion, which is 334 kilojoule per Kelvin. So we have that there. So, but here is kilojoule, but now we've converted it to joule by adding 30. The same thing here, 2256, is in kilojoule. We added 30 to make sure that it's in joule per kilogram. Now the reason for that is so that we can be consistent, because this one is already in 4190 joule per kilogram per Kelvin. So we want to that one is in joule. So we need to make sure that every other thing is in joule as well. So this one requires a change in temperature. So 100 minus 0, which is this. So we use M change specific capacity delta T. So all of the remaining thing to do is to just punch that carefully into your calculator, then add them together. You have the total energy required to perform the operation. So, and I think that's the end of the session for number 6, and I think that's the end of the revision. And I'm not sure, Pisca, do you understand that, or do you have any question? Is that okay, Pisca? Good, that's fine. Now, finally, now for recommendation for exam revision. Now, I will want to emphasize, please, everybody, for those who are with me now, for those who will be listening to this video later on, ensure you understand all practice questions. All the practice questions I've given to you, everyone that you already have on your blackboard, and I know I gave you some of them during the study week. Ensure you understand all of them. All of them, very, very important. Understand all the practice questions. That is number one. Excuse me, please. Then secondly, ensure you understand all the questions in the module coursework. Your coursework, excuse me. So it's getting hotter here because of I'm talking about the exam now. Sorry. So for your module coursework, ensure you understand all the questions I've given to you for your module coursework. Ensure you understand them. And then finally, ensure you understand the last all the questions in the exam question. Practice them. I gave you the question is on Blackboard. Make sure you understand all the questions given to you then. And again, try and familiarize yourself with the formula sheet in that question as well. With that and everything you have on Blackboard, read the principle, then go to the questions. And I'm sure this video will be of help as well. And I think that's the end of the revision. And I thank you for finding time, even despite the technological problems, the issues, and you still find time to join me again. And any questions? Yeah, Pisca, yes? Yes, it's sometimes because somebody want to give me a very good work. You want to this is a question here saying, can I use pencil instead of pen? Yes, you could use pencil instead of because it's easier. You want to in the exam, so it's easier. Maybe you want to clean to make sure that your work is neat. But I really want to have the final answer in pen because sometimes the only way to show that this is it's not a problem. We are not careless with your exam sheet. But sometimes pencil can get clean due to if the pencil is not. I'm not really sure. But pen is permanent. You know what I mean? But if you could, I've seen a student writing with pencil, and then after the fellow was sure of what he's done, now he now write on pen. You now write on pen on top of it. That's fine, but I would not say I'm not going to penalize you because I'm sure I really understand what you're trying to do. You want to make sure that your work is neat. But to be honest, I want to say if you go for pen, that's perfect. Pen is perfect. If you make any mistake, all you need to do is let me just show you. Let me show you. If I'm trying to solve a problem, because I'm like you, I understand what you're trying to say. If I'm trying to solve a problem, I say S equals Y plus Z. Oh, I want to write A, it's not Z. All you need to do is just to cross out. If you cross out, write neatly underneath, that's fine for me. I will not penalize you for crossing out this. I will not penalize. I will not. Sorry, I will not penalize. You will not be penalized. I will not penalize you for this. So if I know some people hate that. I know some people hate that. I understand that. But if you just a neat one, a single line, cut just a single line, it's fine. For me, I won't penalize you. I can follow what you are doing, and I know it's exam. It's exam. In the coursework, I am very strict. You need to be neat. You need to be this. You need to be that. You need to present your diagram very neatly. But in the exam, I don't look for that because exam condition is exam condition. You don't have all the time. But when you have your coursework, something you have with you for a month, I expect a perfect job to be done. But exam, if you look at some. Even handwriting sometimes can be very difficult to read in the exam, but we are trained to see what you have written, whether it is poorly written or whether we are trained to see it. So we need to follow everything you've done. So I would say pen is better, but there's no specific rule that say pencil will be rejected. Does that answer that question? Okay, Chris, you have any question, Chris? I should say thank you for your time. You've done well. Thank you very much. Thank you very, very much. Once the video is ready, the video is ready, I will share that on the Blackboard. I'm sorry. Thank you for the applause, Chris. What I'm going to do, I wanted to share the video on Blackboard, but there's a problem. The Blackboard will not be available for, is it Monday now? So what I'm thinking of doing is to upload it on YouTube. So if I upload it on YouTube, I know YouTube is available every time. So once you have the link, the YouTube link, I think that will be perfect. Okay? Thank you. Thank you, everybody. Thank you. Thank you. So if you log on, you need to log on for Yavenda, you need to log on. You need to close it so that I can close it here as well. Yavenda? Good, thank you.